Last class, we learned about bonding. We learned about covalent bonding and ionic bonding. So ionic bonding, remember, is when you've got the formal transfer of electrons. So a metal giving away electrons to a nonmetal, like this with magnesium and nitrogen. So our magnesium has 2 valence electrons because it's in the second column, the second group. And our nitrogen has 5 because it's in the 5A15 group. And so magnesium can give away 2 electrons to the nitrogen, and then it needs some more from another magnesium, and it's a whole complicated, like, giving electrons away. It's not a particularly effective way to find formulas, since we can just do the swap and drop, like with Mg2 plus and N3 minus, because we already know their charges. So we can pretty quickly come to the formula unit, or the formula. Nope. Okay. Was apparently lifting. Okay, so we did that, and then we also learned about covalent bonding. And covalent bonding is more exciting because it's new. And so with covalent bonding, what we are looking for is octets. All of our atoms want 8, count them, 8 electrons. And the way that covalent bonding works is that they're sharing electrons. A minimum of 2 electrons are being shared, and we usually represent it as a single line. And the shared electrons count for both of the things that are attached. So these 2 electrons count for the hydrogen's duet. They also count for the oxygen's octet. We learned about single bonds. We learned about double bonds. And double bonds, as you might expect, are stronger than single bonds. They're also shorter than single bonds because we can think of them like rubber bands. The more rubber bands that you have around 2 things, the closer that they would get together, assuming that they're repelling each other. And we were alluding to, teasing, triple bonds. So nitrogen, we just talked about, has 5 valence electrons. So if we have 2 nitrogens next to each other, if we share 1 pair of electrons, initially we had 5, we gain 1 because now we're sharing with the neighboring nitrogen. So now we would be up to 6. And 6 is not satisfactory. So we can share another one to get up to 7. So now we're sharing 2 electrons, so we've got a double bond. And we are still not up to our octet, right? We're at 7. 5 plus 1 is 7. And so we need another one. And so we do a third bond. And at that point, we've got 8. And so the way that we would probably rewrite this, just to make it look nice and clean, is nitrogen. We've got our 2 nitrogens. They've got a lone pair each, and they've got 3 lines between them. We've got the little hamburger menu, as it's formally called. In this case, it's a triple bond. So 3 lines, 3 bonds. How many electrons are in this triple bond? 6, because we've got 3 bonds, 2 electrons per bond. So we've got 6 electrons. So 6 electrons there, 2 electrons in each of the lone pairs. So our nitrogen on the left has 8 electrons. Our nitrogen on the right also has 8 electrons. So they are both happy. They've got their full octets. Crazy things are happening. So we've got our octets. They've got their 8 electrons. And that is a triple bond. A triple bond is when 3 pairs of electrons are shared between 2 atoms. A pair, of course, being 2 electrons. Triple bonds are even shorter and stronger than double bonds, because now instead of 2 bonds, we've got 3 bonds. 3 is stronger than 2. And the distance is also shorter. So the distance in a nitrogen-nitrogen triple bond, is 110 picometers. In a double bond, it's more like 124. The big takeaways here: more bonds is stronger than fewer bonds. It's also shorter than fewer bonds. And because nitrogen is a diatomic molecule and it's got this very strong, very short triple bond, it's relatively unreactive as a molecule, which is great, because then you can put it in your coffee, your cold brew, you can put it in your Guinness, you can put it in other things, you can just generally have it around and it's not a big deal, it's not a problem. So if you like nitro cold brew, it's got nitrogen bubbles instead of CO2 bubbles, and since nitrogen is unreactive, it doesn't change the flavor of what you're drinking, which is cool. So if we want to write Lewis structures for covalent compounds, we've got some rules. So the first thing that we want to do is draw the skeleton. So we want a skeletal structure just showing the relative positions of the atoms, and we've got some subsets of rules for this. So our hydrogen atoms are always, always, always terminal atoms. They are on the end. They're only going to be attached to one other atom because they need a duet, which is 2 electrons. One bond is 2 electrons. So hydrogen can only form one bond. So it must be on the end. You can't put it between two things. Also, many molecules tend to be symmetrical because it's more stable. And so when a molecule contains several atoms of the same type, the same element, they tend to be in terminal positions, or we tend to have some mirroring between the left and the right, or the top and the bottom, or however you choose to draw it. We're also generally going to avoid drawing things in ring structures. There are some instances where we can draw stuff in rings, but usually you need at least 5 atoms in the ring. If you get like, some people like to put little triangles. Triangles tend to explode. So we're not going to be putting any triangles. Those will just blow up. So we're not doing that. Okay, so that's our first step. We want to just draw out like where is everything. And then once we've got everything drawn up, once we've got all of our elements, the number of atoms of each element that we've got, then we want to calculate the total number of electrons. Please note that this is valence electrons, because valence electrons are the ones that engage in bonding. So these are the outermost shell, the highest n number. For those of you that remember back to last week, the highest n number of our electrons. So looking at the rows that they're in. And again, this is based on the group that they're in. So it's equal to the group number minus the 1 in front for some of them. So anything that's in the P block, we're going to subtract that 1 that's in the front. So group 13 turns into group 3. Group 17 turns into group 7, 7 valence electrons. And we will occasionally have ions, so charged particles. Electrons are negatively charged. You may remember. And since electrons are negatively charged, we're going to add 1 electron for each negative charge. We won't do a ton of stuff with ions. Mostly we'll be dealing with neutral molecules, but they will come up a couple of times. So once we've summed up our valence electrons, once we've got our VEs all calculated up, then we want to distribute electrons among our atoms. To start, we want to get all of our pieces connected. So remember, for our first step, we just got everything put up on the board in order for those to all be in a molecule, they have to be connected. And so we need to get some bonds, some lines drawn between some of those atoms. And these are the bonding electrons. Are BEs. And when I do BEs, I'm talking about the minimum number of bonding electrons. So this is just like part of the process of getting everything connected. How many bonding electrons do we need to connect everything? So we're going to start off with 2 electrons between each pair of atoms. And again, we're going to avoid small rings. I don't think that we've got any ring structures in the class, probably. And again, things that have really small rings, like 3 or 4 members, tend to explode. They're very unstable. They don't like doing that. Okay, so this is the minimum number of bonding electrons once we've got pairs between each of our pairs. 2 electrons between each pair. Then we're going to distribute the remaining electrons. So the remaining electrons I usually label as Re. This is just whatever we've got left over. So we take our number of valence electrons, that's our total number of electrons to play with. We had to get everything connected together, so we subtract out our bonding electrons, and that gives us our remaining electrons, which we can place in as dots. And we do have a lot of examples, so if you're sweating, take a jacket off. But we've also got examples coming. And so our goal, when we're placing our remaining electrons, is that we're going to place them on our terminal atoms, our outside atoms first, and then we're going to work our way inward towards the center. And we want to give octets to as many atoms as possible. This will not always get us to full octets. So if we're not getting to full octets from this, then we can form extra bonds. Since bonds are sharing electrons, they're covalent bonds. That lets us share, like if we've got something that's got an octet, it can donate a pair of electrons in to form a bond and then add electrons to something else. We should see some examples of that coming up. But what we're not going to do is add in or make up extra electrons. Any questions so far about this very fun game that we're going to play? Cool. Let's do some examples. We've already seen the Lewis structure for H2O, but let's just use it as a practice for doing a Lewis structure. So the first thing that we want to do is just get all of our pieces on the board, all of our elements. So we need a skeletal structure that's got 2 hydrogens and 1 oxygen. Our hydrogens have to be terminal, and so our oxygen will have to go in the middle. So we've got HOH, and we need to know how many valence electrons do we have. So we've got our skeletal structure, and then we need valence electrons. So for our valence electrons, for hydrogen, we've got 2 of them with 1 electron each. For our oxygen, we've got 1 of them, and oxygen has 6 valence electrons because it's in that 6A or 16 column or group. So our hydrogens are giving us 2, our oxygen is giving us 6, and so that gives us a total of 8 valence electrons. So we've got 8 dots that we can put on our little playing board here. Once we've got our valence electrons, in order for this to actually be a molecule, we have to get everything connected. So we need to place some bonds in. Our hydrogens can bond in with our oxygen. How many bonds have we placed? 2 bonds. How many electrons have we placed? 4. Each bond is 2 electrons, so 2 bonds is 4 electrons. So subtract out 4 bonding electrons, and we've got 4 remaining electrons. We've got 4 more electrons to place everything to its full octets. Do we need to give hydrogen, either of them, any more electrons? We do not. Hydrogen is happy with one bond. It's happy with a duet. So hydrogens are good. H is happy with 2 electrons. So our remaining 4 electrons can go onto our oxygen as 2 lone pairs. And once we've placed those 2 lone pairs, we've got no electrons left. Is our oxygen happy? Yes, our oxygen is happy because it's got an octet. Just closing the door real quick. Perfect. Okay. So our oxygen's happy. We've placed all our electrons, and that means that this is, hopefully, probably, a good Lewis structure. Questions about the process? Okay. Let's do one for H2CO. So for H2CO, our first step is that we need the spooky, scary skeletal structure. Very seasonally appropriate. For our skeletal structure, we're going to need our hydrogens to be on the outside. And I don't expect you to be able to come up with necessarily the correct way to place these, so I'm going to give you the skeletal structure. So this way would work. There's probably also a universe in which bonding like you could definitely flip the oxygen and carbon and come up with a Lewis structure that seems correct based on our knowledge. You might also be able to just put the whole thing on a line. It's not as symmetrical if you just put it in a line, though. It's like we've got this nice left-right symmetry if we have it placed this way. Okay, so that's our skeletal structure. And then we need to count up our valence electrons. So we're looking for, we've got 2 hydrogens. So we've got 2 of those, and they've got 1 electron each. So our hydrogens are contributing 2 electrons. We've also got a carbon, and carbon has 4 valence electrons. We've only got 1 of them, so it's just 4 electrons. And our oxygen has 6 valence electrons, just like on the previous slide. Again, we've only got 1 of them. So we've got a total of 2 plus 4 plus 6 is 12 valence electrons. Then we have to connect everything. So in order for it to be a molecule, everything's got to be connected. So our hydrogens need to connect. They can connect to our carbon. Our carbon can connect to our oxygen. How many bonds have we placed? 3 bonds, but we placed 6 electrons. So minus 6 bonding electrons, which leaves us with 6 remaining electrons. So let's go through and check where can we place these electrons. Do our hydrogens need any more electrons? No, they don't. Our hydrogens are good. Our other terminal atom is our oxygen because it's only connected to the carbon. So our oxygen is also a terminal atom. How many electrons can we add to our oxygen? How many electrons does our oxygen have towards its octet? It has 2, because it only has 1 bond. So oxygen has 2 electrons before we do anything with our remaining electrons. So how many electrons can we add to our oxygen? What would be the maximum amount? What's our goal? Our goal is an octet, which is 8 electrons. We've got 2, so we can add 6. Because the octet is 8. So we'll add those in. Bink, 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 bink. And we've placed 6 electrons. That was all of the electrons that we had. Right, so we subtract out those 6 electrons. This is just bookkeeping to make sure that we don't add too many or leave some off the board. So all of our electrons are now on the board. So let's go through and check our octets. We already established that our hydrogens were happy because they've got their 1 bond, they've got their duet. Does our oxygen have 8 electrons? Yes. It has 1, 2, 3 lone pairs, which is a total of 6 electrons, 6 dots. It also has 1 bond, which is another 2, so it's got a full octet. Does our carbon have an octet? It does not. It has 3 bonds with 2 electrons each. Only 6 electrons. Carbon is not happy. Where can we find some extra electrons to share with our carbon? Our oxygen has some lone pairs. It's got some electrons that it's keeping all to itself. And so through the power of friendship, we can share one of those pairs of electrons to form a double bond. And so our structure will turn into something that looks like this. We didn't do anything with our hydrogens, so our hydrogens are still good. Is our oxygen still good? Does it have 8 electrons? Yes, it does. It's got 1, 2, 3, 4 in the lone pairs, and it's got another 4 from the 2 bonds. So our oxygen is happy, and our carbon has 4 bonds, 2 between carbon and oxygen, and then the ones to the hydrogens also. And so our carbon is also happy. Questions about any of that? Okay. We can also have polyatomic ions. So remember that thing that I was saying about ions earlier, where if it's negatively charged, we add 1 electron. If it's positively charged, we subtract 1 electron. That's what we're doing here. So polyatomic ions, like any of our things that end in ate or ite, are oxyanions. Those would all fall under the domain of polyatomic ions. And so we're going to have additional adjustments to our electrons because we also have now charge. And when we do a Lewis structure for a polyatomic ion, we are going to do it inside of brackets and write the charge in the upper right corner outside the brackets, like we did with our ionic compounds. So it's the same as if we did an ionic compound. right? We put the brackets and we put the charge in the top right corner. This time we've just got more stuff involved. Okay, one of our smallest polyatomic ions, Cn-, the cyanide ion. For this one, the skeletal structure is pretty easy. As long as you don't put them on top of each other, it's good, because we've just got 2 points. If you put them on top of each other, it's just very confusing, and I'm using the wrong colors. Okay, C, N. So we've got our carbon, we've got our nitrogen. We need to count up our valence electrons. Carbon, we've got one of them, 4 electrons. Nitrogen has 5 electrons, valence electrons. We've just got one of them. And what else? It's negatively charged. So we've also got a 1- charge, which means 1 electron. If you don't add in that 1 electron for the negative charge, you will not get a good Lewis structure. So we've got a total of 10 valence electrons to play with, thanks to that negative charge. To get everything connected, we've just got 2 things. We need 1 bond to connect them. So we're going to subtract 2 bonding electrons for our 1 bond. We have 8 remaining electrons. Where can we add our 8 remaining electrons? There's 2 options that I can imagine well, more than 2 options, but there's 2 reasonable options that you could come up with. Where could we put some electrons? Carbon. How many electrons should we give carbon? We could give carbon 6. We have 8 electrons, we've got 2 atoms. So my inclination would be to donate them equally. You don't necessarily have to do it that way. You could also get the right Lewis structure if you gave them all to carbon. So minus 8 electrons because we placed 8 more dots. So we've got no electrons left. All our playing pieces are on the board. And we need to go through and check our octets because octets is the goal. So looking at our carbon, we've got 1, 2, 3, 4, 5, 6. 6 electrons, which is not an octet. Carbon's not happy. Nitrogen also has 1, 2, 3, 4, 5, 6. 6 electrons. It is also not happy. Where can we find some more electrons for our carbon and for our nitrogen? From each other. The power of friendship. So our carbon has 2 lone pairs. Our nitrogen has 2 lone pairs. Lone pairs are things that we can move in to form bonds. So let's do that. Let's move in 1 of these lone pairs and see what happens. Okay, so we move in 1 lone pair. Carbon has how many electrons counted toward its octet? It's got the 2 in the lone pair. It's got 4 in the bond, the double bond. So it's got 6. Nitrogen has 2 in each of its lone pairs, so 4, plus 4 more in the double bond. So nitrogen is actually good now. So carbon is going to need some more electron action, and it can get that action from nitrogen. So nitrogen can share in one of its lone pairs. And that would look like this. So we add in a third bond. And now if we do our checks, carbon has 2 electrons in its lone pair, plus 6 in its triple bond. So carbon has 8. Nitrogen also has 8 because it has the same situation. It's got the 1 lone pair, which is 2 electrons. It's also got 3 bonds. Each of those lines represents 1 bond. Each bond is 2 electrons. So it's got an octet. So our octets are good. Are we done? We're not done. What are we missing? Charge. Da-da-da-da-da. Brackets, and then a 1 minus outside in the upper right corner. Now are we done? Yes, we are done. Questions? Confusions? Smart remarks? Okay, and keep going then. Another polyatomic ion, this one for you to try. So please write the Lewis structure for the ClO- ion, and feel free to discuss with your neighbor. Okay. Lewis structure for the hypochlorite ion. Starting off with our skeletal structure, chlorine, oxygen. Just get them out there. And then we need our valence electron count. Chlorine contributes 7 electrons. We've only got 1 of them. Oxygen contributes 6 electrons because they're in the 7A. Adjusting. Stupid laser pointer. Okay, the outrageously bright green one then instead. Okay, so chlorine is in the 7A, oxygen's in the 6A, so they've got 7 and 6 valence electrons respectively. And what else? Charge. 1 negative charge. 1 negative charge equals 1 electron. So we've got a total of 14 valence electrons to place. To get everything connected, we need 1 bond. So subtract out our 2 bonding electrons, and we will have 12 remaining electrons. We can evenly split our 12 electrons between our oxygen, our chlorine, and our oxygen. They've each got room for 6 more. So we give them 3 lone pairs. So 6 electrons to our chlorine, 6 electrons to the oxygen. We've got no electrons left. So once all of our electrons are placed, let's look for our octets, see if they're complete. So for our chlorine, we've got 2, 4, 6, plus 2 more in the bond is 8. Chlorine has its full octet. Oxygen in the same 2, 4, 6, 8 electrons. So oxygen's done. And then all that's left is brackets and the charge. So you give it the big brackets and put the negative outside in the upper right-hand corner. questions on that one?
Why are the brackets around both as opposed to just the O?
They're around both because the whole thing together has a 1 negative charge. It's not like localized on the oxygen or the chlorine, as far as we know. Okay, there are also some exceptions to the octet rule. For example, there are some Lewis structures that we just cannot write a good Lewis structure. Things with odd numbers of electrons, some of these molecules exist in nature, we're going to ignore them. We would just do the best that we can. So for example, NO, nitrogen has 5 valence electrons, oxygen has 6. If you add those up, you get 11 valence electrons, which is an odd number. And so the best that you'd be able to do is getting nitrogen having that lone electron on it, and then oxygen has its full octet. We don't have the rules to say why this is the best structure, but that's as good as we can get, one of them being 7 electrons instead of an octet, and the other one having an octet. There's also another fun exception, which is boron. So boron tends to form compounds with only 6 electrons. Aluminum can also do this. So boron and aluminum can form compounds with only 6 electrons on the boron/aluminum. So for example, boron trifluoride, boron and 3 fluorines, or boron trihydride. The boron has 2, 4, 6 electrons. It does not have a full octet. It is actually happy with just 6 electrons in its valence shell. Aluminum can also do that sometimes. We also have some other exceptions to the octet rule. So some larger elements can have more than 8 electrons around them in their Lewis structures. So for example, SF6 and PCl5, the sulfur in the middle has 6 bonds, which would give it 12 valence electrons. The phosphorus here has 10 electrons, and we call these expanded octets. So this is when we have more than 8 electrons. It's bigger than an octet. On the Lewis structure worksheet, which I'll post at some point, there's a section for expanded octets. So unless I tell you that there's expanded octets by putting it in that section that says expanded octets, we're just going to assume that everything takes normal octets. If you're curious about why expanded octets exist, I'd be happy to explain that to you. Just come and ask. It's beyond the scope of the class. Any questions before we jump into resonance? So again, boron, aluminum are happy with only 6. We can have expanded octets, but those will only be in, like, specifically, this is an expanded octet situation, like it'll be described to you. Okay, so when we do Lewis structures for some things like SO2, we can write more than one good Lewis structure. So if we were going to do a Lewis structure, we would come up with sulfur being in the middle. And sulfur is in the middle because it's more balanced. So we've got better symmetry. We've got left-right symmetry. If we put the sulfur on the end, either the left end or the right end, then we don't have that symmetry, and nature tends to like symmetry. We've got 18 valence electrons, because each of these has 6. 6 from each of our oxygens. Sulfur also has 6. We'd get everything connected. with our 4 bonding electrons, and then that leaves us with 14 remaining electrons. And we would start by giving those to our terminal oxygens, 6 to each. And then we would have 2 left over, and we would give those to sulfur. Kind of rushing through it so that we can get to the point of the slide, which is resonance. Okay, so we get here, and if we check our octets, our oxygen on the left has 2, 4, 6, 8 electrons. Great. Our oxygen on the right is in the same situation, so it also has a complete octet. Our sulfur in the middle has a lone pair and 2 bonds, so 2, 4, 6 electrons. It needs 2 more electrons to get its octet. Where can we get 2 more electrons for our sulfur? Yeah, we can get them from our oxygen. Do we take them from the left oxygen or from the right oxygen? So we could take from left, or in orange, go Giants, the right. So which one do we choose? Left or right? The answer may surprise you, it's yes. So for resonance, we can make 2 equally good Lewis structures. And so what I mean by yes is we do both. Why make a choice when you can have it both ways? So we've got an option for taking in from the right and from the left. Let me clean these up a little bit. Okay, so this is what it would look like. From the left would be this green line in the bottom figure. From the right would be the top line, the orange Go Giants figure. So these are equally good Lewis structures. You may notice that they're just flipped, they're just mirror opposites. In reality, nature is not really going to choose between taking electrons in from the left or the right. It's going to do some sort of weird average of the two. We don't have a way to draw the average. And so what we do instead is we say it'll do both, and we do a little arrow between it. So it's going to be rapidly going back and forth between the two of these. It's like if you take a picture at a given moment, you might see that it looks like this top one. If you took a picture later, it might look like this bottom one, the left one. So we draw both, and we do the little double-headed arrow to show that it's actually both of these, and it's moving back and forth between them. So that's what we call resonance structures. So either of those 2 Lewis structures that we drew out for SO2 predicts that we would contain 2 different kinds of bonds, one double bond and one single bond. And when we look at SO2 in nature, we find that both of the bonds are intermediate in strength. So it's more like a 1.5 strength bond. And so what we're doing, what reality is doing, is we're taking these 2 Lewis structures and we're merging them together. And so it's kind of like if you breed cats. So if you mix 2 cats together, right, the cat that you get out should look like both of the parents. It would be some sort of hybrid. And so that's what we're doing, but for molecules. Yes. So the bonds are equivalent. And so we just draw this double-headed arrow. Questions about resonance structures? there are structures that have more than 2 resonance structures. You can get at least 4, possibly more, depending on what structure, what the compound is. We're generally not going to be doing those because it's just like a lot of unnecessary redrawing of things. Okay, let's combine all of the stuff that we've learned to draw the no 2- ion, which is nitrite. Please include resonance structures. Okay, structure for NO2-. To start, we want a skeletal structure. Any ideas for our skeletal structure? Did you say ONO? Oh no. So our structure is oh no. So that would be our skeletal structure because it gives us symmetry between the left and the right. It wouldn't be no or un because that wouldn't have the same amount of symmetry. And then we need to tally up our electrons. We've got 1 nitrogen that's got 5 electrons it's bringing to the table. We've got oxygen. We've got 2 of them, and they're each bringing 6 electrons to the table, which is 12 electrons. And we also have a 1- charge. And that 1- charge means that we add in 1 more electron. So we've got a total of 5 plus 12 is 17, plus 1 more is 18 valence electrons. To get everything connected, we need bonds between our oxygens and our nitrogens, which is 2 bonds. 2 bonds is 4 electrons. Again, the Be here is just the minimum bonding electrons, just to get everything connected. And then after that, we've got 14 remaining electrons. Anyone getting a little bit of deja vu? So we can distribute our 14 remaining electrons. We can give 6 to each of our oxygens, because they currently have 2. Adding 6 will get them up to their octets. Okay, so good octets. So 12 electrons to our oxygens. And we need 2 more. We can give that to our nitrogen. You may notice that our nitrogen has 2 bonds, which is 4 electrons, plus another 2 electrons from the lone pair. So we are in a 6 electron situation, and we need to bring in some outside help. We can bring in electrons from the left or from the right. So let's clean this up. Okay, so we bring in electrons from the left, or we bring in electrons from the right. These will get our octets all filled. So we've got our 2 perfectly good, equally good structures. Those are our resonance structures. How do we indicate that it's both? What are we missing? The double-headed arrow. So we add in the double arrow, and we're done. Unless they're charged, and so we also need brackets. And now we're really done. Any questions? Okay, on to the next building block. So resonance structures, there are couple that show up on the Lewis structure worksheet. For the most part, it's normal, just like one good resonance or one good Lewis structure that'll show up on the worksheet. One of the things that we are going to use this for, use the Lewis theory for, it's not just for putting together molecules, although that is kind of fun, but we also want to be able to predict the shape of molecules. And so for predicting the shape, what do they look like in 3 dimensions? We are using valence shell, electron pair, repulsion theory. What is the valence shell? Which electrons are those? Those are the outside electrons. Those are the ones that we're using for bonding. So the ones that we're using for bonding also are lone pairs. So valence shell. What's an electron pair? What's a pair? Just 2 things, 2 electrons together. We've got a couple things that constitute an electron pair. We've got lone pairs, like on our oxygens here. We've also got bonds. Bonds are also electron pairs. So the electron pairs that we're talking about here are lone pairs, LPs, and bonds, single, double, or triple. And repulsion just meaning that they push each other away or repel. So we've just described what the entirety of the theory is, in essence. Our outside electrons, the one that we use for bonding, the lone pairs that are made up of those electrons push each other away. That's all that valence shell electron pair repulsion theory or Vicepper theory is. And we can use this to predict the shape of molecules. So the basic idea is all of our electrons are negatively charged. All of our electron groups then are going to repel each other, and they are going to spread out as much as possible. The things that count as one electron group are a lone pair, a single bond, a double bond, and a triple bond. Those all count as one electron group, because the triple bond, those electrons are all grouped together. The double bond, they're also grouped together, it's just fewer electrons. So the electron groups want to spread out as much as possible. And that's what they do. So for our Vicepper, or valence shell electron pair repulsion theory, we can predict shapes. So for example, we can predict the shape of CO2 carbon dioxide, which has this Lewis structure. So the carbon is double bonded to each of the oxygens. So the carbon has 2 groups on it, 2 double bonds. We're primarily focusing on the central atom because that determines the shape. So our central atom is carbon, and it has 2 groups. The furthest that 2 groups can get away from each other is on opposite sides. So we're spreading our electron groups as far away as they possibly can, which gives me a great opportunity to T-pose on the class. So CO2 has a linear geometry. And the theoretical bond angle of 180 degrees. They've gotten away from each other as far as they possibly can. Anything else, especially if you've just got 2 things, we're just going to call it linear. Some places don't call it linear. I call it linear. But anytime that we've got stuff that's all lined up, that's linear. Other shapes, we saw H2CO earlier. This was one of our first examples. It was our second example. On the carbon, we have 3 groups. We've got 3 electron groups. We've got 2 single bonds, and we've also got a double bond. So those are 3 different groups. And the 3 electron groups form what is called trigonal planar geometry. The bond angles are about 120 degrees. You may recognize the tri on the front of trigonal, which means 3. And then I think gonal, like trigonal, means 3 points. So it's got 3 points that stick out. And then the planar part here means that it's flat. Flat or in a plane. Not like an airplane, but like the XY plane in math, plane. Okay, so that's going to have the YMCA pose if your feet are together. This is our trigonal planar geometry. Notice that if I turn sideways, I'm as flat as I can be, given that I am a 3-dimensional being. So that's our trigonal planar geometry. Now, what happens if we add another one? So if we add another one, right, we've got carbon in the center here, and it's got 4 bonds on it. So you might expect to form this like X shape, which we would call square planar. However, we live in 3 dimensions, and so it's actually a little bit more spread out. If we take that X shape and we turn, like from the torso, 90 degrees, now the hands can get a little further away from each other because they're not all in the same plane. And so this is the tetrahedral geometry. In a square planar geometry, like we've got it drawn here, where it's flat on the board, you get bond angles of 90 degrees. But if you get into this tetrahedral geometry, you get a little bit more room with 109.5 degrees, roughly. And this tetrahedral shape, the tetra is 4, and the hedra side, or the hedra bit, is sides. So this is the shape of a D4. If you like connect the H's and make it faces. Or you can just remember that it's 4 things, and that also works for this class. Questions about our first 3 shapes? So those are our first 3 shapes. We also have some other shapes. So we've been looking at things that don't have lone pairs. We've been looking at things that only have atoms attached to the central atom. So for something like NH3, ammonia, we have 4 electron groups. So we've got 3 bonds, and we've got a lone pair. So we've got 4 groups. So our electron geometry, the way that our electron groups are shaped up, right? We had our X pose, and then we turn 90 degrees. This is our electron geometry. So if we're including the electron lone pair, then this is our shape. However, that lone pair doesn't really take up space. So we get tetrahedral for our electron geometry, but for our molecular geometry, the shape of the actual molecule, if we subtract out the lone pairs, then if we hit that X and turn, and then we get rid of one of those groups, notice that I've got 3 points. My feet are still on the ground, and my hand is kind of off to the side. So it's still trigonal, because I've got 3 points, but it's not lined up, because this lone pair is pushing my hand out of the plane. And so what we get is still called trigonal, because it's got 3 things on it, but it's pyramidal, not flat. Right? It's more of a pyramid shape. So hit that X, and then get rid of one group, and like if we did it this way, you can see kind of looks like a pyramid now. I could have also done that on the wall, but it's not as fun. So these 3 groups, the bonding pairs, get pushed out of being flat because of the lone pair. So our electron geometry includes our lone pairs. Our molecular geometry excludes or removes the lone pairs. And we also have one more shape that we're going to talk about before we end for today. So for H2O, which we've also seen today, if we look at our oxygen, we've got 1, 2, 3, 4 electron groups. 4 electron groups. Hit our X, turn 90 degrees. But now we're getting rid of 2 of the groups. I'm going to get rid of my hands because I'm not very good at floating. Still working on that one. And so if we look at the shape between my torso and my legs, they're not linear. I couldn't show you that if I wanted to. It's a bent shape. So they're pushed out of linear for the molecular geometry, and so we call this a bent shape. There's also a way that we can get a bent shape if you've got 3 groups. So if we've got a central atom, I'm just going to call these A for atom. And if we have a lone pair on the end, this will also give us the bent shape. So we're doing our Y of YMCA, and we get rid of one of the groups. It's still a bent shape instead of a linear shape. Any questions before we stop? Cool.